Okay, so here we want to look at 6.2.1, and on this particular problem we want to use Gaussian elimination to find the complete solution to the following system of equations or show that none exist. And so first let's write our augmented matrix, which the first row gives us the coefficients of x. Second row gives us the coefficients of y. The third row gives us the coefficients of z. And the fourth column, so these first column, coefficients of x, second column, coefficients of y, third column, coefficients of z, fourth column are the constants that are on the opposite side of each equation from the coefficients of the variables. Alright, so that's our augmented matrix. And first thing I'm going to do, first row operation I'm going to do is I am going to interchange row 1 and row 2. And typically, in row 3. Typically that's how I would write that operation. So on the next matrix, that's the row operation. And the reason I'm doing that is because that already has a 1 in the first row, first column position. And I may not keep that 1, but it makes it really easy for me to have a 1 in that anchor row as I begin this process of elimination. So I may not preserve that 1 as I do my steps. Alright, now so the process is to start in column 1 and get zeros on the non-diagonal elements in column 1. So the diagonal element in column 1 is the element that's in row 1. And so notice what I'm going to do here to get my next matrix is I am going to change row 2. So I'm going to recopy row 1. Not making any changes. That's my anchor row. So I'm going to recopy that and not change that row at all. And I'm going to use that row first to change row 2, then to change row 3. And so what I'm going to do is I'm going to multiply -2 times row 1, and I'm going to add that to row 2. And that's how I'm going to get my new row 2. So -2 times 1 plus 2 is 0. -2 times 2 plus 5 is 1. -2 times -5 plus 4 is 14. -2 times 1 plus -8 is -10. And now I'm going to multiply -5 times row 1 and add that to row 3 to get my new row 3. So notice what I'm doing. I'm getting my zeros in column 1 first, then I'm going to get my zeros in column 2, then I'm going to get my zeros in column 3, and then I'll worry about getting the 1s. Now I have some 1s that have showed up here, but those aren't necessarily going to stick around. It depends on what processes I'll need for my other zeros as I work to get the reduced echelon form of my matrix. So negative 5 times 1 plus 5 is 0. Negative 5 times 2 plus 12 is 2. Negative 5 times negative 5 plus 3 is 28. Negative 5 times 1 plus 12 is 7. All right, now I want to get my zeros in column 2. So column 2 and row 2, since I'm in column 2, row 2 will be my anchor row, and I want to get a 0 in column 2 in row 1 and in row 3. So when I'm in a column, I never change the row that has the same value as the column whose zeros I'm trying to obtain. All right, so I'm working in column 2 now, and I want to get my zeros in row 1 and row 3 of column 2. And row 2 is my anchor row. That's the row that's not going to change. So I'm going to copy row 2 from the previous matrix. And now I'm going to work on getting my zeros in column 2, row 1, and row 3. All right, so I need to move this up a little so we can see. Let me zoom out just a little bit. Okay, well, I'll have to. All right, so I'm going to multiply negative 2 times row 2 and add that to row 1 to get the 0 that I need there. So negative 2 times 0 plus 1 is 1. Negative 2 times 1 plus 2 is 0. Negative 2 times 14, that's negative 28, plus negative 5 is negative 33. Negative 2 times negative 10 plus 1 is 21. So that's my new row 1. Now I want to get my new row 3. And I am also going to be multiplying negative 2 times row 2 again and adding that to row 3. So negative 2 times 0 plus 0 is 0. Negative 2 times 1 plus 2 is 0. Negative 2 times 14 is negative 28. Plus 28 is 0. So I'm looking at the previous matrix, and I'm multiplying negative 2 times row 2 of the previous matrix, which is the same as row 2 in this matrix, since row 2 is my anchor row, and I'm adding that to row 3 of the previous matrix. Now, as soon as I see I've gotten all zeros left of my vertical dividing line, I know that my system is either going to be dependent or inconsistent. If I get a 0 entry in this row right of the dividing line, then the system is dependent. If I get anything other than a 0 here, the system is inconsistent, because I'll be saying essentially 0 equals a non-zero number, which is of course false. So let's see what happens. So negative 2 times negative 10 is 20, plus 7 is 27. And the point of this is, as soon as you get all zeros left of the vertical dividing line and a non-zero in that same row right of the dividing line, you stop working, no need to continue, conclude that the system is inconsistent, and the solution set is the empty set. And notice that what this row 3 is telling me that I have in this final matrix, this row 3 is telling me that 0x plus 0y plus 0z is simply 0 equals 27, which is false. And so this is always what an inconsistent system will have when you are row reducing the matrix. It will have a row that has all zeros left of the dividing line and a non-zero right of the dividing line on that same row.